Welcome to this presentation entitled Movement Through Fire Smoke, Past Research and Current Standards Development. My name is Daniel Nilsson and I'm from the University of Canterbury, and I've done this research together with Carl Fridolf from VSP in Sweden. The outline of the presentation is as follows. I will start with a bit of a background. I will then tell you about past research in this area. And then finally, I'll tell you about standards development that is currently ongoing in this area. And I'll give you a very brief summary of the presentation. Now, visibility is often used in performance-based fire safety engineering design as a tolerability criteria. You might see in legislation that you sometimes use 5 meters of visibility, sometimes 10 meters of visibility, but it is commonly used as a tolerability criteria. At these levels, people don't actually slow down. So in most cases, it's not a problem. However, there are cases, specific buildings like rail tunnels, road tunnels, or complex buildings where you don't use this tolerability criteria, but instead you allow the visibility to be much lower. Now, if you do that, you need to represent the movement speed in fire smoke in a realistic way. Problem is, there is no standardized approach for doing this, so it's typically on a project-to-project basis, which means that there is an inconsistent level of safety. So one road tunnel might not be as safe as another road tunnel since you use different correlations. So there is definitely a need for a standardized approach for representing movement speed in fire smoke. Now, in this area, there's been quite a bit of research. One of the early studies was done by Yin in 1978. So Yin did experiments where people walked through smoke and real fire smoke. So he filled a corridor with smoke, 2 types of smoke, and he had people walk through it and he measured their movement speed. So Yin used something called irritant smoke and then non-irritant smoke and got results that look like this. And you might be familiar with this graph since it's been spread all over the world. And basically this is the data that Yin got from his experiments, and you see as the extinction coefficient goes up, basically the smoke becomes denser, then the movement speed goes down. You can see in this graph that he did 2 experiments, one with wood crib fire smoke, and that's the irritant smoke, and then the kerosene fire, which was the non-irritant smoke. Now, the conclusions that Yin was able to draw based on this was that people move slower as the smoke density increases. So if you look at the graph here, you have the extinction coefficient. As the extinction coefficient goes up, then the visibility goes down. If the extinction coefficient reduces, then the visibility increases. And you can see a downward trend here. So as the smoke density increases, people slow down. He also saw that irritancy was quite important. So more irritant fire smoke seems to reduce people's movement speed quite a bit more. So those were some of the conclusions that Yin drew from his study. More recent studies, like the one by Francis and Nilsson, haven't used actual fire smoke, but instead use artificial smoke. So the study by Francis and Nilsson was in a smoke-filled road tunnel, or a mock-up of a road tunnel, and they got similar results as Yin. Now, what was used here was artificial smoke, basically glycerols, like party smoke, and acetic acid. And the reason why acetic acid was used was to get some irritation of the eyes and nose and upper respiratory tract. And as I said, the results were similar to Yin's, so you could see a reduction of movement speed as the density of the smoke increased, or the visibility decreased. And the main conclusions from this study was that, one, same as Yin, smoke seems to slow people down, but there were also some other trends that were observed. So behavior patterns, how people follow the walls to find their way to safety, relying more on their perception of touch than their visual impressions. Now, perhaps one of the most interesting recent studies in this area is the one by Fridolf, Nilsson, Francis, Ronke, and Arias from 2016, where the authors compiled data from a lot of publications up until 2016. And they did a lot of data compilation, but perhaps the most interesting for this presentation is what they did with movement speed versus smoke density. So they looked at what people had done in different experiments around the world, and they compiled it into one single graph that I'll show you in a minute. Now, they were very careful when selecting studies, so they wanted studies that were similar. So it ended up being mainly tunnel-related studies, so people walking in corridor configurations or tunnel-like configurations, with the same type of smoke, and it usually was an artificial smoke with sometimes some type of mild irritant like acetic acid. They also only compared experiments where they had the same lighting conditions. So there were some experiments where it was completely dark, they weren't really relevant, so they had similar lighting conditions in these experiments. Now, this is what the data looked like. So when they compiled everything in their report, it looked something like this. So you had movement speed on one axis and then extinction coefficient on the other. Now, extinction coefficients was typically what was reported in the different studies. The main reason for that is it's easy to measure. You have a light source, you have a light receiver, and you measure how much of the emitted light that is at the receiver. And that gives you a measure of the extinction coefficient. Now, what Friedolf et al. Asked themselves in their study was, well, is it really relevant to present the extinction coefficient? The extinction coefficient might be easy to measure, but it doesn't really govern how people move. It's the visibility that governs how you move. Since if you have 3 meters of visibility, you move at a certain speed. If it's 5 meters, you move faster, and so on. The other question they asked themselves is, well, is there a direct correlation between extinction coefficient and visibility? And there are equations. But the thing is, there are 2 different equations for light-emitting objects, like if you're moving towards a light, or light-reflecting objects, like you're moving towards a lit wall. And the principle is that if you're moving towards a light, you can actually see the light quite far through the smoke, but a lit wall, due to intensity, you can't really see it until you're very close. So, in some experiments, people were moving towards lit emergency exit signs. In others, they were just moving towards an end of a corridor. So, the visibility conditions are not really the same, since if you have a lit exit sign that you're moving towards, you see that nothing is between you and the exit sign. Hence, in that particular case, you might have a longer visibility than if you're moving towards a lit wall. So they tried to convert everything and make it comparable, and they converted everything to visibility. And this is what the data looked like once they've compiled everything. So you can see here all the data points that remained, and you see the correlation between visibility and movement speed. And as you can see in the graph, when you have 10 meters of visibility, people don't really slow down. They move at their unimpeded movement speed. But then at about 3 to 4 meters of visibility, people start slowing down since they can't see the very far in front of them, and they might be afraid of bumping into things, so they start slowing down. And then at about 1 meter visibility or half meter visibility, basically they move at a very, very slow pace. So this is really interesting. If you want to know more, read Friedolf et al.'s publication. It's published in Swedish in a report, as well as in papers, scientific peer-reviewed papers. Now, we've talked about the background, I've talked about past research. I'm now going to tell you about current standards development, and then I'm going to give you a very short summary. Now, in ISO TC92 SE4, which is the group on fire safety engineering, there is currently a standard being developed, namely ISO TS for Technical Specification 21602. Now, the working title of this document, since it's still in the review process, the working title is Estimating the Reduction in Movement Speed Based on Visibility and Irritant Species Concentration. And the objective of the standard is to give the designer some guidance on how to handle movement through fire smoke if you need to include it in your performance-based design. Now, I'm going to use the graph from Friedolf et al. To illustrate how the standard works, but basically it's a 4-step process. So 4 steps you need to consider to represent movement speed in fire smoke. First of all, when you do your calculations for your population or your occupant, you have to decide your unimpeded movement speed. And your assumption is that people move at their unimpeded movement speed until the visibility becomes low enough for them to have to slow down. So you typically have a curve describing when that happens, and when the unimpeded movement speed hits that point on the curve, people start reducing their movement speed. So step two is that the movement speed is reduced as a function of visibility. The lower the visibility, the slower people walk in smoke, since they're afraid of bumping into things. And as they're moving slower and slower, sometimes what happens is that you get irritants, and you get sufficient amounts of irritants to irritate the eyes, and the eyes start tearing up and people can't move anymore. And in the standard, that is also included. So if a certain irritancy threshold is reached, then it's assumed that people slow down instantly to a lowest movement speed, which is similar to the movement speed you would have in complete darkness. And it's typically the analogy here, why do we move at that low movement speed? It is as same as in darkness, that at that movement speed you could still collide with things without injuring yourself. So people slow down. They don't stop moving, but they move really, really slow. Now, in the standard, there are basically 3 different methods for how to take account of movement speed due to visibility. The method 1 is called deterministic approach individual. This is used if you're using a risk analysis approach, which is deterministic, which means that you're using worst credible case thinking, worst credible case scenarios in your design. So the curves here that are given in method 1 are quite conservative. It's also deterministic analysis when you have one person. So for a road tunnel, it could be a Norwegian road tunnel with just a couple of cars every hour. So it's typically 1 or 2 cars in the tunnel and quite limited number of individuals evacuating. So then you can use method 1. Method 2 is still for deterministic analysis, so still when you have worst credible case thinking, but in this case it's when you have more people in the tunnel, for example. And what you're given in this method is not just one curve, but actually one conservative, one slightly more conservative, and one ultra-conservative curve. And you can sort of sample from these 3 curves in your deterministic analysis to get a bit of variation in the movement speed. The final method, method 3, is called probabilistic analysis, or is used for probabilistic approaches. So that's when you do a probabilistic risk analysis, and rather than being one curve, you actually get a distribution of curves, and you can sample from these and distribute them to your occupants in your design. Now, how is movement speed versus irritancy treated? Well, it's treated the same way for all methods currently in the standard. So basically you calculate the fractional effective concentration according to the standard ISO 13571, the 2012 edition. And if the FEC value, fractional effective concentration, is above 0.1, you assume that people move at the lowest possible movement speed, which is 0.2. And that's similar to the movement speed in complete darkness. Now, to give you a short summary of this presentation, I started off by giving you a bit of the background behind this, why this research is needed and why the standard is needed. I then told you about past research, starting with Yin and then ending with the study by Friedolf et al. From 2016, where a lot of the data available was compiled in one single report. And then finally, I told you about the most recent standard being developed in ISO on movement through smoke. And the intent of the standard is to give designers guidance on how to handle movement through smoke in performance-based fire safety engineering design.
Yeah, this is interesting. After we've recently implemented that movement speed change in smoke in Pathfinder, so it's good to see your talk in context of that feature.
Okay.
Maybe some room for us to allow for some tweaking of the function to some amount for the user to have some control over it.
So you're including the effective visibility as well as irritants, or mainly visibility?
Right now, it's just soot visibility, calculated visibility from soot. Mm-hmm.
Yep.
All right, welcome everybody back. So we'll see here. Here they come. So as you come back into session, if you have any questions for Daniel, please post here in chat. I'll also check some of the other chats just to see. Sometimes people ask in the event or the stage chat. We have to find that for you.
Okay.
So we have one here from Daniel Swenson. It says, in a real fire, we would expect the smoke to be layered. A small change in sampling height can lead to a large change in visibility. Do the experiments include this effect? And are there any other comments on the importance of layering?
I would say the experiments, most of the ones I'm familiar with are a tunnel context, and a lot of them are artificial smoke. So it is a relatively well mixed condition. What is measured, though, in most cases, is the visibility at eye height, typical eye height. So anything from 1.5 to 1.8 meters in most of the cases. And you do get a bit of layering in the experiments, even if it's cold smoke, but it's not a lot, to be honest. And also, if you're looking at the tunnel scenario, you get, at least further away from the fire, you get a relatively well-mixed environment anyway. So,
okay. And then there's another comment here, a question. Is it fair to use a very conservative speed, like 0.8 meters per second, throughout the whole fire condition? And would you recommend doing that?
You can definitely use it at the unimpeded. I would still probably reduce it as you get the really high density. So it's hard to find the exact value for when it starts decreasing, but typically it seems to be around 3 to 4 meters where people start to slow down. So according to the methodology used in the ISO standard, you can definitely choose your own unimpeded speed, but I would still suggest reducing it as the smoke density increases, and particularly also take account of irritancy, since once the irritants kick in, then people start moving really slowly. So it's not 0.8, it's rather 0.2, maybe 0.3 meters per second.
Okay, that's interesting. So would you say then would there be basically 2 separate curves with and without irritant gases, maybe?
There would be. We've looked at this quite a bit, and looking at irritants is actually quite complex, since you don't have a lot of experiments, at least not in recent years, that properly included irritants. But what it seems to be is that you focus on the visibility first, and then you monitor the irritancy, and once the irritancy hits a threshold, then you instantly slow down the movement speed and people start moving really, really slow. Since there seems to be a relatively quick transition from no irritation at all to quite heavy irritation of the eyes. So I would treat it as sort of look at visibility first and then monitor the irritancy level. And once the FEC value, in our case, we use the FEC value of 0.1 in the standard, that's what's proposed. When that kicks in, then people pretty much instantly start to move really, really slow.
Interesting. Okay. Another question here, just commenting, really like the graph showing speed versus visibility, but he's asking himself, in current evacuation models such as EVAC, that consider already this in the calculation? If they consider this. Yeah, just that if current evacuation models such as EVAC consider visibility and speed relationship in the calculation. I know that Pathfinder does have that capability. I'm not, and I think FDS EVAC does too. Yeah,
they do. So they do include it. What we've seen, and so you can include it yourself as well. I mean, you can implement it yourself if you're using a model and use your own correlation. What the standard aims to achieve is to get a sort of a unified approach to how you do it. Since what we've seen from infrastructure project, in my context is mainly the Swedish context, is that depending on the consultancy firm and depending on who does the analysis, you use the different curve. And what the standard tries to achieve is that you should use pretty much the same curve in all infrastructure projects, so it doesn't rely on who's the consultant or what model you're using.
Right. Last question here for our session. So just great talk. Heian Chong says she's one of our speakers. Great talk, and apologies. The next talk may have some repetition. Is there a point where the conservative speed is too conservative? There are other data sets where a low visibility has shown higher walking speeds, meaning that people are running with Bohr and Tsuki.
We've seen that as well. So if you get a reduction in visibility, but it's not a huge reduction in visibility. People do tend to speed up. Now, the question, however, is if you're doing a performance-based design, that you should choose that higher speed, or if you should be using a conservative value, since yes, people do speed up, but I'm not sure that that's the value we should use in design. Maybe we should be on the conservative side, so not everyone speeds up.
So you might get a bonus in real life where you get some
Exactly.
extra evacuation rate, but let's
Absolutely.
not plan for it. Yeah, fair
Exactly.
enough.
That's my view.
Great. Well, thank you very much, Daniel. Thanks for the talk.
Thank you.
Great Q&A. Appreciate it, and we'll see you around. Take care.
See you. Bye.